everybody. I'm delighted to welcome Dr. Jen Wojcik to the call. Dr. Wojcik is a member of the PAGE Consortium, and as you may know, the PAGE data is now in our VCI as a reference for allele frequencies in rare population groups. So thanks again, Jen, for joining us today, and please just go ahead whenever you're ready. Really appreciate it.
Sure, thank you. So I prepared slides to introduce you to the PAGE network or PAGE study. PAGE stands for Population Architecture Using Genomics and Epidemiology, and so it's a collaboration between both geneticists and epidemiologists in the field. And I've structured it to give you mostly background as to what the data is and sort of the motivation going into the creation of the data. Feel free to interrupt me whenever you have any questions. I know there were a few questions that I got in an email already, and so I've tried to address them all. But if you have anything else that pops up or any questions, just let me know. Oh boy. Okay. So the entire motivation behind the PAGE network is that in the United States, a disproportionate level of chronic disease is found in minority populations. And this is not reflected in our research. The majority of genetic studies have been done in groups of European descent, whether it is white Americans or in European populations. And therefore, the benefits of this genomic medicine and the large advances that have happened in genomic medicine don't always make it into the populations that need it the most. And again, this is sort of seen in many of the large-scale genetic studies that we have out today. UK Biobank is 94% white British specifically. These other large studies, these are published and posted estimates, are overwhelmingly of European descent. And so, there has been a lot of progress over the last, 10, 15 years, I guess. And so what I'm showing you here is the GWAS catalog is a resource that is maintained by EMBL as well as NCBI here. And what it does is take all the published GWAS, so the genome-wide association studies. And what I'm showing here on the left-hand side is, of all the published studies, what is the mean sample size for these different ethnic groups? And as you can see, the first GWAS was in 2005, and it has, the sample sizes have been getting larger and larger and larger, and the mean size has been getting larger and larger. And what you see is the other groups, such as Asian, Hispanic, Latino, African or African American, and Native American, the mean size is much, much smaller than the European descent groups, and it has stagnated over the past 6 years or so. You see there's been some progress in the 2008 to 2011, 11, 12, and then since then it's really stagnated for most of the groups. And then you see on the right the median size, which is something I think a little bit, so we have a lot of really large studies, but we still have regular moderate studies being published as well, and here you see that it really has stagnated. The median sample size for these groups really has stagnated since 2012, and so despite a lot of push for diversity in genomics and diversity in GWAS, it really hasn't been borne out in, I think both the participant level, but also the studies that have been published. And this is for numerous reasons, but the main reason why this is a problem is because of the disproportionate number of discoveries and associations that are found in these groups. So as of mid-2018, when this was published, 78% of the individuals in the catalog were European descent, but 76% of the associations were due to the European descent. And what I think is really interesting from these numbers is that you see for the European and Asian populations, they have the two largest proportions of individuals as well as studies in this catalog. But you see that for the Hispanic Latin American and the African and African American groups, despite only having 1.3 and 2.4% of individuals in these studies, they do have 4% and 7% respectively of the associations. They do almost produce these a larger proportion of associations, disproportionate things. So there's something to say that there is something that besides the social justice sort of slant of this motivation, there's also a statistical and a biological reason why you can discover more variations and more associations in these populations. And it's really important to note that this is not representative of the United States demographics. And it is especially not representative of the global demographic. So depending on what your reach is for what your research wants to do, what representative population you have, this is really not portable to other groups internationally. And I think something that is really important to think about on the clinical side of things is that it often takes years for discoveries to go from GWAS or basic sciences to the clinic in these translational aspects. And this is becoming more and more of a gap because the population is not static in the United States. As more of the U.S. minorities become majority in the next several decades, I think the gap is just going to widen and widen. Okay, so that's sort of the motivation to why this study was developed. The background I'm going to give to you fit into sort of 3 different categories just so that you know what's coming down the line. The first is the study design. There were a lot of questions as to who the participants are on PAGE, how they were recruited, what outcomes they had, sort of the basic epi of those individuals. And so I'll give you that background. The second little block is about the array design. So all the individuals were genotyped on a new genotyping array that was developed by our groups as well as a collaboration with other groups and Illumina. And so I'll give you an idea of what went into that design as well as sort of the quality control metrics we did to get a subset of those sites. And then lastly, I want to give you a brief background as to what the populations in PAGE would look like after we had their genotype data, and how we came up with the group definitions that are published now in the VCI. There are 2 sort of levels of granularity that are available for these frequencies. On the University of Chicago browser site, there you can do both a broad set of frequencies and a narrow one, or you will soon. But for interpretation, I think the broad ones, which are the 11 categories that have previously been presented to this group, made more sense because they are the large groups and therefore the most stable estimate. All right. Okay, so who is PAGE? So PAGE is a multi-center collaborative effort. We just wrapped up the 2nd iteration of PAGE, so PAGE 2. And what it is 3 different longitudinal cohorts. This is a women's health initiative that is PI right now is out of Fred Hutch in Seattle, Charles Cooperberg, and Ricky Peters. And then we have multi-ethnic cohort study, which is at USC with Chris Hyman and University of Hawaii with Lois Marchand. And then on the east we have Carrie North at UNC with the Hispanic Community Health Study and Study of Latinos at UNC, and then we have 1 metropolitan biobank, which is based in New York City at the Mount Sinai School of Medicine. This is BioMe. This is with Ruth Luce and Emer Kenny. And so because it's such a collaborative effort, it required a lot of coordinating, and so I'm speaking as one of the members of the Coordinating Center at Stanford, and we are with the Coordinating Center at Rutgers, which is Tara Matisse and Steve Beiske. Funding came from NHGRI and NIMHD, the National Institute of Minority Health and Disparities. And the genotyping was done at CIDR in Baltimore, and then some of the University of Washington at their Genome Analysis Center. Okay, so I'm going to give you just 4 brief slides as to what all of the longitudinal cohorts are and the biobank. These are all pre-existing studies. PAGE was brought together by NHGRI to bring together all of the samples that a lot of EPI studies sort of ignore because they're smaller sample sizes, they introduce heterogeneity into their studies, and so that really brought all of these samples that were underutilized in their home cohorts and home studies into this larger group effort. The first one I wanted to share with you is Women's Health Initiative, this WHI. This is a this has few arms, but the majority of it is a longitudinal cohort, an observational study. There are several clinical trials as well with it. Clinical trials are for mostly hormone replacement therapy. I think there were some vitamin D trials as well. But the main study was from 1993 to 2005 with 2 different extensions on top of that. But 162,000 women. They are older women, so between the ages of 50 and 79 at enrollment. Between 93 and 98. And they were followed from mostly, these main outcomes I've listed here. So these are cardiovascular outcomes, cancer outcomes, as well as fractures. But they do have a lot of information about your basic anthropometric measurements, so height and weight. We do have information about different biomarkers, so lipids and other things like that. And so they do provide a really rich resource. This is a pre-existing cohort. All right. And then next we have a metropolitan biobank. So this is a Mount Sinai biobank. Recruitment started in 2007. There's about approximately 35,000 patients enrolled with this, and this is increasing. And this is a biobank at the Institute of Personalized Medicine, and it draws from the entire New York City metropolitan area, from this entire health system, and it's all linked to their electronic health records. So this sort of has both your basic demographic info and metrics, but also whatever happens in the course of their health care is also linked to this. Next is a community health study and study of Latinos. This is out of UNC with Cary North. These are longitudinal cohorts. The recruitment happened between 2008 and 2011 of about 16,000 individuals in 4 communities. So they're split up into 4,000 people at each one of these sites: Bronx in New York, Chicago, Miami, and San Diego. The breakdown here is much wider than the Women's Health Initiative in terms of longitudinal cohort, where a third of the participants are between 18 and 44, and then the rest are between 45 and 74. And it should be important to note that these individuals were sampled within households. They do have families and related individuals in this. But for the sake of the frequencies, those related individuals were removed from downstream frequency analyses. And so the outcomes here were primarily to identify risk factors in the development of cardiovascular disease in these communities. But they do have other questionnaires as to diet and basic measurements of the clinic over time as well. And then lastly, we have the multi-ethnic cohort that goes into this. This is Chris Hyman at USC and Logan Marchand at University of Hawaii. Again, a longitudinal cohort. Recruitment began in 1993, and the biospecimen collection, including the DNA collection, was in 1996 moving forward. This is a very large study, approximately 215,000 women, and a lot of the information does come from questionnaires on their medical history, medication usage, family history, but they also have some follow-up visits. And all of the incident cancer cases are by regular linkage to Hawaii Tumor Registry and the LA County Cancer Surveillance Center. So this is the SEER registries. Okay. So when all of these different groups came together and were able to contribute a substantial number of samples to this, this is how the breakdown looks. This is self-identified race ethnicity. These are what the participants identify themselves as. And you see that 22,250 are Hispanic Latino, so nearly half of our participants out of the 50,000 total are Hispanic Latino individuals. Then we have 17,000 approximately African American individuals in the study. And then we have smaller groups of other sort of self-identified groups. So we have approximately 4,700 Asian individuals, 3,900 Native Hawaiian individuals from Hawaii, and then 653 Native American. And it should be noted that the Native American samples were not sampled in conjunction with any sort of tribal sample or community. These are individuals who self-identify as Native American within metropolitan areas, or whatever the collection sites were. And so we also have 1,000 individuals that classify themselves as others when given the options. A large proportion of individuals are actually South Asian, which we can see from their genetics, but they just didn't feel like any of the other labels were appropriate for them, so they would mark other. And this also includes individuals of mixed ancestries and people who just didn't see themselves in any of the labels that were provided. Okay, so the PAGE network as a whole is 50,000 individuals with a focus on U.S. minority populations. So before, there are a lot of traits that we have harmonized together. I'm not going to talk about the GWAS that we've done in this talk because it's not really relevant, I think, to the allele frequencies. But there is a preprint available online if you're interested more, and I'm happy to answer questions about this after as well. What we did was harmonize 26 different traits. This gives you an idea as to what the traits are that we have available within PAGE. They span things from inflammation and lipids and these biomarkers and these things that we can measure from samples, to lifestyle aspects like cigarettes per day, amount of coffee they have, anthropometric measurements. And so you see there's a wide range in these measurements that we have and the ability to do GWAS on these 26 traits in a very large non-European descent group. So one of the questions I got was what the age distribution was within PAGE. And so I showed you before how the recruitment happened. And so WHI, Women's Health Initiative, did have older women as recruitment. And so you do see that reflected in the distribution of ages for the, when you go look at self-identified race and ethnicity. And what you see here is that individuals who identify as other or mixed tend to be younger individuals. So are the Hispanic Latino individuals. You see sort of a skew to the left. And this is also because of the sampling. So this is not necessarily reflective, obviously, of demographics in the United States, but rather the sampling and the way the studies were set up. But you see that it's a very good overlap for most of the individuals. And there was very little difference in terms of sex besides sampling center. So obviously the Women's Health Initiative is all female, while the other sites are both female and male. Okay. So additionally, for PAGE, we were able to genotype 55 additional reference populations. So when we were developing PAGE and bringing all people together, a very important aspect for us was to be able to estimate the ancestry of these individuals fairly accurately and to really be able to disentangle the relationship between ancestry and the genetic epi of these traits. And so the sort of sampling of where the populations come from in this group, the majority of these individuals were taken from the HGDP, which is the Human Genome Diversity Panel. It's a reference panel that has previously been genotyped but not on this chip. As you see them here, there's also some populations that were added in to fill in gaps. So these include populations from South Africa, Honduras, Mexico. This provides a well-rounded look as to global variation. Now, I should note this isn't everybody. You will see there are gaps in the representation for these populations, but we do a lot better than the standard, and we do fill in some gaps that are previously left by other reference panels, such as 1,000 genomes. Okay. So I'm going to move now into the array, those populations we had, and one of the biggest challenges we had moving forward is that a lot of the previous developed genotyping arrays were developed for one population at a time, most of the time European descent groups. The way that you decide which sites to genotype depends heavily on your reference genome. And so for a long time, the reference genome was of a European descent individual, and so therefore that's where the variation was taken from. And then there was another wave in the early 2010s, hold on a second, where there were some additional arrays developed for non-European descent groups, but they were only for one at a time. So you had a Latin American chip, you had an African variation chip, an East Asian variation chip. But for us, that wouldn't work because we have 50,000 individuals from everywhere, really, and therefore we need one chip to sort of capture everybody simultaneously. And so this is really important moving forward, and we've seen this borne out in how the field has moved since the development of the chip. This was developed in 2014. And since then, a lot of these large-scale epi studies as well as these biobanks have been developed, and they require, for collaboration between sites as well as within sites, a single array that could provide information across many populations. So for PAGE, we had, you might want to say, the beta testing of the chip as part of our deliverables, and so this is now marketed as the multi-ethnic global array, and a smaller version of it is marketed today as the global screening array through Illumina. But this is Mega, the consortium version. We wanted the chip to be not just a GWAS scaffold, but sort of a multi-use tool for genomics in health. So we have various buckets of content loosely fitting into 3 categories. So you have your standard scaffold, which is what you would typically see on a GWAS chip, which has sites that were selected to represent variation in different groups to provide very broad, sort of your typical GWAS in terms of resolution for mapping, trait mapping, and this includes Illumina Human Core, the African Diaspora Power Chip, which was a development by Kappa, and Illumina for specifically African variation that wasn't found in previous iterations of reference panels. And then we developed this trans-ethnic GWAS scaffold, another additional 360,000 sites. And then we also have exome content. This includes Illumina's, before they had the human exome, the exome chips, that's on there, as well as exonic variants that were selected to be representative of Hispanic, Latino, and African American populations. And then we had 40,000 variants that were functional variants, which I'll go into more in a bit, but these were any variants that really have shown any indication of being relevant to human health, according to numerous databases at that time. This was as of 2014. And then we also had some custom content that was more to do with spine mapping for our studies. So before I go into what the actual content was, it's really important to know that there was extensive quality control done on this genotyping. Because it was a new chip and a very multi-ethnic study, numerous waves were done to ensure that the genotypes we had at the end of this were accurate. And so the genotype calling was done at the Centers for Inherited Disease Research in Baltimore on Illumina's Mega. Rare variants were followed up manual with Z-call and then a manual curation. There were several technical filters that would eliminate many sites. This included that being very rare with a low call rate. The heterozygous rate, so the heterozygote rate was above 80% in the sample. It was dropped as well. Within each of these plates, there were duplicate samples plated, and so any replicate errors for those sites were dropped. Cluster separation within Genome Studio had to be above 20%. If there were any gender differences in the call rate, the number of heterozygotes, the number of homozygotes, those sites were also dropped because that's indicative of errors. So once we had all of the raw genotypes called, they were sent over to the Genome Analysis Center at the University of Washington. Here, sex discrepancies were removed for samples. Chromosomal abnormalities were zeroed out of the genotypes. They were dropped. And then there were some more standard GWAS quality control filters that were put in place. So this includes missingness above 2%. Those were dropped. Batch effects were assessed across this. Duplicate discordance was assessed again, as well as Mendelian errors was assessed here. So within our samples, we do have some trios and some families, and so we were able to assess for these sites if there are some errors within the families. That would give us an additional check. And then again, we did population Hardy-Weinberg equilibrium thresholds, looking for these really error. So they had to be really out of whack to be filtered here. And this is population specific based on self-identified race and ethnicity. And I'll go into a little bit later why I keep on saying self-identified for this context, but it was really important for us to always have that in mind. So the next round of QC was done here at Stanford. We removed any sites that were redundant. So there were several sites that were sort of mapping the same exact variant, and those were removed. Due to this being a product that was in development originally, we developed this in-house with Illumina. There were some minor issues with the probes, so any probes that didn't map to anywhere in the genome or mapped hundreds of times in the genome, they were all removed. Everything was moved to the plus strand to make everything consistent with current reference panels. We updated the coordinates, and then there were some sites where the probes didn't match the actual RFIDs. These were also removed. And then for especially the clinical variation, we would actually go back and check the intensity. So we have all the intensity files in-house, and while it is computationally intensive for this number of individuals, we can pull out different sites and check them. So on the right-hand side, you see an example of where the cluster separation is really good on the top, and it's really bad at the bottom. And so we would have dropped the site on the bottom. Okay. So when it comes to the functional variants that I've mentioned before, this includes high-value variants from medical databases. This includes ClinGen, ACMG genes and the variants, PharmGKB, HEMD. And so what you see here, this is after some genotyping, and you have 22,000 variants that are present in ClinVar at the time. We got these from ClinVar, as well as smaller buckets from these other databases. And so we wanted to have broad representation of these sites. We tried to get as many on as possible. They were disease or outcome agnostic, and so it really was anything in the database that could be mapped within our chip. Okay, and if we look at, these are the ClinVar assertions, and what you see is that we do have representation of all clinical assertions across the different categories here, and you see that about half of them are, or not half of them, but a large percentage of them are pathogenic, according to the 2014 version that was downloaded, and then a large number were benign, and we have distribution within the other categories as well. Okay. So I keep on hammering in, once now we have the samples, we have the genotypes, and so we can look at the populations. And for us, it was really important to understand the relationship between self-identified race, ethnicity, and genetic ancestry. And so what you see here is the principal components plot. Each one of these dots is an individual, and they've been colored by how they self-identify. And so we did actually have 40 Europeans that snuck into there at some point. They are on this plot. But you can orient yourself by saying, on the right-hand side, this is the African component. So individuals closer to this centroid are going to have more African ancestry. At the top, you have more East Asian ancestry. This is being pulled apart here. Towards the back left, these are the Americas, so indigenous ancestry to the Americas, Native American ancestry. At the bottom, you have Europe. So this is where the European ancestry is. And so it's really important for us to note that these groups are not discrete. On average, they do have differences. But one of the very first things you do in the GWAS QC process, you look for outliers. So you say, okay, this person identifies as Asian. Do they fall in genetic space with the Asian group that you would expect? And what we found is that that wasn't really possible for most of these groups because there was a spectrum and there wasn't a clear cutoff as saying, oh, this is obviously an outlier, this is not. And I think this really emphasizes the complications that arise when we talk about genetic ancestry and race ethnicity, is that there is, I wouldn't say a conflict between the two, but it isn't a straight one-to-one. And so for us, we went ahead with all these analyses with their self-identified race ethnicity. And it should be noted that for our actual GWAS, we didn't stratify. We combined everybody in models that would appropriately account for the population substructure as well as the relatedness. And again, this is because these groups are not discrete. And this is especially true because these are admixed individuals. So a lot of these groups in the United States do have ancestry from multiple continents. And so what we see right here is that, typically you see that first principal component and the second principal component. If we extend it to the third, you can really see the multidimensionality of the diversity in these groups. That individuals fall not just between 2 different ancestries, 3 different ancestries, but 4 different ancestries in this space. And if I would extend it out to further dimensions, you would see the same thing, where you don't have these clear 2-dimensional or even 3-dimensional individuals, but these individuals have ancestry that is very complex from different groups. And again, each one of these dots is a person, and they've been colored by how they self-identify. Okay. So this is another way of depicting a very similar idea, and you have principal component 1 on the left-hand side, all the way to principal component 9 on the right-hand side, and each one of these lines is an individual, and again, colored by how they self-identify. And what you can see right here is that the first PC, which I showed you before, differentiates between African ancestry and non-African ancestry. Principal component 3 differentiates between Native American ancestry and non-Native American ancestry. PC4, this is the Hawaiian and Pacific Islander component that comes out. PC5 is South Asian, as you can see up there. And they are colored as other, but there are several individuals who identify as coming from India, especially in the Mount Sinai Biobank, so we can sort of see where they fall there. And then later components, you see the difference between Hispanic Latino groups. And so what we do see is that, although the later principal components do capture a smaller proportion of the variance in these groups, they are very important, and you see differentiation between them. Okay, so going back to this, the almost half of us are Hispanic Latino, while the rest are African American and other groups. And this is important because within the Hispanic Latino group, they were also provided the ability to self-identify further granular labels. And so, for the sake of granularity here, some of them have been collapsed, but about 6,200 individuals are Mexican or Mexican American, 3,600 Puerto Rican. Then we have smaller groups of Dominican, Cuban, and those are the most granular way they can identify. And then some collapsed labels are South American. About 1,000 individuals are from South America broadly, and then 1,400 Central American. And then we have, 1,400 individuals who identify as being more than one of these groups or other. And so these are the labels that go into the allele frequencies that we provided. And again, there was a question as to how these groups were defined, and everything that we presented has been self-identified. Okay. And the reason, again, why we have self-identified is that even when it comes to groups, there's no separation, and we see this with the Hispanic Latino group. They're no different. And so what you have here is the later PCs. From the left to the right, you have a Caribbean client, so it's Cuban to Dominican to Puerto Rican. And then from top to bottom, you have Mexican, Central American, and South American. And so while you do see differences on average in these groups, they are a spectrum and sort of covered over the entire space. Okay. Another way of looking at PAGE with admixture is to look at the proportion of the person's genome that comes from different continents. And so each individual here is a vertical line, and it has been colored by the proportion of their ancestry due to these specific backgrounds. Right here I've only highlighted for you Native American ancestry, European ancestry, and African ancestry. On the left-hand side, you see African Americans. Our estimates are consistent with other studies where it's on average about 80% African ancestry versus 20% European. And then you have Native American in the center there with a large group of Hispanic Latino, Asian, and Native Hawaiian. And what's really important for us to emphasize here is this Hispanic Latino group. So you would have noticed that in the 11 population labels, the Hispanic Latino group is really the only one that gets broken down into more granular labels in terms of on a country or a territory basis. And so here you have, I've split it up by how they self-identify. So you have Cuban, Puerto Rican, Mexican, Dominican, Central, South American. There's mixed individuals, and there's New York City individuals that were unclassified. And what you see is that, on average, Mexican and Mexican American individuals have more Native American ancestry. The Cuban individuals in the study have more European ancestry on average, and Dominicans have more African ancestry. And this is really consistent with prior evidence. And it's really important to note that if you picked a single individual from this, you wouldn't be able to tell necessarily where they came from. But there are differences on average. I think that's a distinction that needs to be made when looking at this sort of evidence. All right. And sort of give you a summary of this. This is average proportions of continental ancestry in these different groups. And again, you see much more Native American ancestry within Mexican American individuals and South American individuals. Much more European ancestry in the Cuban individuals and Puerto Rican, and then much more African and Dominicans, and that is sort of expected. And again, I'm just going to not spend too much time on here, but it's just another way of looking at it, where you see individuals, when you look at these three different kinds of ancestry they could have, three different continents, they do fall differently, and you do see differences between the Caribbean individuals, so primarily of European and African descent due to demographic history and the history in these regions. And then you have the continents, where it's mostly Native American and European, again, due to the historical migrations and colonialization. Okay, so this brings us to our 11 discrete categories based on self-report. These were broadly African American, Asian, Native American, Native Hawaiian, and South Asian. And then, of course, the Latino group, they're broken down into Central American, Cuban, Dominican, Mexican, Puerto Rican, and South American. And I hope I've showed you previously why it was really important for us to provide this granularity when possible, because of these differences between populations. Now, I had a few outstanding questions that didn't really fit anywhere else. So I just want to go through these quickly before I sort of wrap up in a second. But there was a question about observation counts, and this is the total number of haplotypes. So it's the total number of haplotypes that went to the calculation. So if we looked at 100 individuals in this group, there should be 200 haplotypes or observation count. I am not sure if things have changed meaning through the different iterations. I don't think I have access to the VCI, so I can't tell you for sure, but that's what it should be. And then we provided minor allele count, which is the number of times that minor allele was observed across all haplotypes. So if there was 100 people and 200 haplotypes, and you see it in 10, the minor allele count is 10, you should have a minor allele frequency of 5%, if that makes sense. So for the data release, there was no cutoff for frequency, so there are monomorphic sites in there. And that should be taken with a grain of salt depending on how large the observation count is for that group. And then it's always possible that patients are linked across a different database. The patients are included in another database, such as EXAC, GNOMAD, 1,000 Genomes. But it's not likely for these based on where they were recruited. We don't think we see any similarities with 1,000 Genomes. I haven't seen any duplicates when I merged the data. But I can't be sure about EXAC and GNOMAD, but it's very unlikely, and if they were, it wouldn't be a large number of people. We don't have quality metrics currently available for page genotypes, but I do have them in-house at Stanford, as well as Rutgers, I think, does as well. So if there are certain sites or groups of sites that investigators are interested in, we can always look them up to let us know sort of what the sites are and sort of what quality metrics you are really interested in. And then a lot of this information is contained at the PAGE study, so www.pagestudy.org. There is also a preprint on bioRxiv of our preliminary GWAS, 26 different traits, and some of the PopGen work. And that should be under, you can just Google my name in there. I think that's it. And I think it's really important to acknowledge here all of the people who worked on this. This is a very collaborative effort, and a very friendly collaborative effort, which is always nice between these different groups. Elena Sorkin did a lot of the clinical variegation work that should be coming out soon in bioRxiv. Krishi New did also a lot of the work, and Emer Kenny, who I don't know if Emer's on the call or not, but led a lot of this work and moving forward, especially a lot of the work moving to be able to translate a lot of these findings to clinical settings and make sure that they span both the epidemiology and public health aspects of things, as well as the clinical translation of these findings. So I think that's all I have for now. Yeah, then I just have extra slides. But I think I'm done a few minutes early, but if anybody has any questions, I'm very happy to answer any questions about the data or page, anything you'd like to know.
Great. Well, thank you so much for a fantastic presentation, Jen. Does anybody have additional questions? Anyone who is using this data in the VCI, are there any outstanding questions there? I know Jen had gone over some of the questions that we had ahead of time and had sent those in, which is really great. Thanks for that. But any additional questions?
Hi, this is Deb. So I may have missed a part of this. I'm sorry, I had to step away for just a little bit. What's the overlap between variants that are in PAGE versus variants that are in ClinVar? So I guess one of my questions is always how clinically related are these variants in terms of like the disease variants we usually work with in ClinVar?
Right. So I think it should be noted that when the genotyping array was developed for PAGE, this was in 2014, so it is a previous iteration of ClinVar, obviously. And so I think, let me see, I think it's about 22,000 that should be overlap between ClinVar as of 2014 and now. But the size might have gotten larger because we do have a lot of exonic variants, and it could have been that we did try to update it for the newest versions of things. So if a variant happened to be on there in another capacity, such as, the regions we had enriched for fine mapping or the exonic content or the GWAS scaffold, we also included it for the VCI release. So it should be at least 20,000 sites that overlap between ClinVar and Mega at 20,000, but it's possible that we did capture sort of by accident any newer iterations as well.
Do you have any sense for how this data has helped in changing variant classifications? I'm not sure if that's something that you'd have access to.
Yeah, I can definitely speak on that. And I don't know if Ema was able to hop on, but I'll speak to it, and if she wants to add on, then that's great. We've been doing a lot of work with these clinical variants, looking at, we do have more, so what I didn't note is that for a subset of individuals, we have more granular data available. So for the Mount Sinai Biobank, participants were asked sort of if they were immigrants, what countries they came from, where their parents came from, their grandparents. And so we do have a finer ability to look at different groups. And so what we've been doing actually is looking at frequencies within these different groups and ways of triaging them. So, if a variant was deemed to be, possibly pathogenic because it has a very rare frequency overall, we do see several variants when you look at other groups are very common, and so therefore it's unlikely that they are the pathogenic causal allele. And so we've been doing a lot of work for that, and we expect the manuscript to be put at least on bioRxiv before ASHG and made publicly available. But that's sort of one aspect of the things we've been doing, and then characterizing population differentiation between these sites. So are there certain sites that are very rare in some groups and very common in other groups? I think it's important for for researchers to be aware of these sites and be flagged in a way. And then also, we've been very fortunate to work with Mount Sinai, and so we can link to their EHRs and do some association analyses for a lot of these variants and see if they're associated with different ICD-9 codes within that health system. And we do see, very nice stories of groups that are underrepresented in biomedical research, especially granular groups. I think you might have shown this before, so I'm not giving anything away, but there's a group called the Garifuna, which all originate from Central America. They actually all descended from a single slave ship that was shipwrecked on the coast of Central America, and there's actually a very large population of these individuals in New York City. And so it's a very interesting group and a really interesting culture as well, but what we do see is elevated frequencies of certain cardiovascular-related variants, and then we also actually see elevated rates of that cardiovascular disease. And so it's really important, we wouldn't, in the broader biobank, we don't see any relationship between this, we don't really see any enrichment, but when you look at these granular groups, you see them, and it would be important, I think, for, triaging patients for screening later on based on these findings. So I hope that gives you sort of a flavor of what the things that we're trying to do on our end with these. And of course, we contributed them to the VCI as well as the University of Chicago Geographic Genome Viewer, I think is what it's called, to help contribute to the broader community, and so it can be a resource for other researchers as well.
Right, so that's really interesting, sort of thinking about how if you were to see increased frequency of a certain variant, you might be, you're comparing that to kind of what the normal frequency of disease is. You might think then that variant is more likely to be benign, but then of course if the disease frequency is increased in that population, then you can have a reason for that. So do we have access to that information? I'm not sure what information we have access to through the VCI.
No, I think the VCI only has these
the
broad
frequencies.
Groups and frequencies, because there was, a lot of these groups, they are smaller, and there was, at this stage at least, there's ongoing dialogue with a lot of communities for the best way to represent their data, because we want to be very sensitive to the fact that because of some of these communities are much smaller, individuals could be identifiable.
Right.
And so that's sort of some of the sensitivities that go into this and working with these historically marginalized communities. And so I think in the future, we don't know yet whether these things will be available. It's sort of an ongoing discussion, but right now the more granular labels for this aren't available. And so,
so what do we do in that case? Like, let's say, you know, I've got this rare variant that I'll be curating in the VCI, and I see that in a page. I mean, should we email you, or like, how should we handle that?
Yeah, so I mean, so I would say that what you do have access to is very important. If you're interested in more of a granular approach to these variants, one thing that is possible is I do think shortly the sort of more granular labels will be available on GGV, which is the University of Chicago Genome Browser. They're just working protections into it right now, so you can't batch download things because there was concerns about privacy. But you know, yeah, if you have any questions, you can definitely email us. We have all of the individual level data. You know, Stanford is, through Carlos on my end, part of ClinGen. And so we're definitely happy to help if you have any questions and you're curating, that we could definitely help with that. There was just a concern right now with making things broadly available, especially in the clinical space, because a lot of these really unique populations do have sensitivities around them. Yeah. But yeah, if you have any questions, definitely you can email us.
Terrific, thank you.
Hey, can you guys hear me okay? My mic wasn't working a bit ago.
Yeah, I can hear you.
Super. Okay, great. Okay, so question. So, so if this variant info in the VCI that's coming from PAGE is all coming from this mega array, I'm reading that to mean that if a variant is absent in PAGE, it doesn't mean that it was necessarily absent among the cohort. It's possible it just wasn't genotyped, correct?
Yes. Yes.
Okay. All right. So another question. So the variants that are defined as heterozygous, was there any allele frequency cutoff for an individual for a variant to be called as heterozygous?
No. So no, there wasn't any frequency cutoff. So you should have monomorphic sites that come through.
So I'm sorry, I don't know what that means. Does that mean like a mosaic variant, like something that's at 10% allele frequency in an individual could have been picked up?
No. So sorry. So we don't actually have any proportions within an individual. I'm just talking within a population.
Okay.
So it was just typed. It's not a genotyping array, so we don't have sequences. We don't have number of reads.
Okay. Okay.
Yeah.
All right. This is making more sense. Okay.
Yeah. So for us, it either is or it isn't.
Yeah.
If that makes sense. Yeah. We don't have the level of information as sequencing.
Okay. Okay. And so another question. So you mentioned the GGV browser. Gosh, I've really tried to utilize this before to try to get more information about some of the variants that are reported as being present in PAGE for some of the variants I've curated.
Yeah.
But I just haven't seen on that website how to find the PAGE frequency data.
So it was there for a hot second, and now it's not. They realized some security flaws in their database. And so they are currently working on that, and hopefully it'll be available shortly. The way you would find it is that when you go to the browser, there's a drop-down menu to pick which data set you want to see. And it will be there. It used to be there, and then they realized that you could batch download things, and there was issues with identifiability. And so they cut that off for right now, but they're working on making that more readily available. So hopefully, any day now, hopefully, fingers crossed, it should be in that drop-down menu.